Welcome to Careless Coder. Today we're going to count to 4,294,967,296, aka 32 bits, on an 8-bit machine. It's going to be a quickie. Everybody loves a nice little quickie, right? So today we're going to carry your baby. Carry the carry. Well, apparently I can carry your baby these days because in the fucked up 2020s, apparently guys can get pregnant. I don't trust the science anymore either. But there are a lot of carry jokes. For example, my wife asked me, "Why do you carry a gun in the house?" And I whispered to her, "It's because of the Decepticons." She laughs, I laugh, Alexa laughs. And I shot Alexa, because you can't trust the Decepticons.
I still function.
And the Decepticons probably also run on 8-bit processors since they're from the 1980s. So they also have to carry the carry. So let's see how we can do that on the Commodore 64 and how long it will take to actually count 32 bits. That should be a quickie. Except it's not. And then for good measure we also do it on the ZX Spectrum. Now usually you know that I use real hardware, but in this case I ran it on simulators because I had to capture the output because it's going to get very, very long and tedious. And I didn't want to have this camera recording a screen and then having to swap out SD cards. Hence the emulation. But you can run the code on your dedicated machine and time it there. So let's jump in and carry the carry. So let's code this up quick and dirty. And yes, this is quick and dirty because we can make it A, faster and B, smaller. I start here at 1000, which is, if you call it in BASIC, with 496. The reason why I did that is because I wanted to do this, print TI dollar, and also at the end print TI dollar. TI dollar is the Jiffy timer. It will count certain cycles, but yeah, it's not really that accurate, and eventually I ended up looking at my Mac clock anyways, because that's how long it takes. And if you actually not use BASIC, you will actually free up 0 page. And that will make the solution that we're coding right now that doesn't use 0 page significantly faster. About 25% maybe? But let's start. So we have a loop. We clear the carry because we're going to use an add carry. Before you use the add carry, you need to clear the carry. That is not done automatically. So we load into A1 the bytes plus 3. What is bytes? Well, that is something we need to define because those are the 4 bytes in memory that will store our 32 bits. So $0, $0, $0, $0, $0. And this, by the way, is kick assembler. You use your notation of your assembler. So basically what this says is bytes. So this is the address that holds bytes plus 1 plus 2 plus 3. So now bytes contains this byte, whatever that byte is. Right? We're going to add with carry 1 to it. And when this is at FF and we add 1, it will become 0 again. But then the carry is set. And then we will need to add 1 to here. But first we need to store this one back because we need that, of course, to be stored. And if the carry is not set, so carry clear, BCC, branch carry clear, then we branch back to loop. But if the carry is set, we just reuse this code. We do this again. Now you can make this more efficient by either creating self-modifying code. That's what I would do, but we haven't discussed self-modifying code. But basically you would just change this byte in memory to reassemble this byte, and etc, etc, etc. But for now we do it quick and dirty. We unroll the code. which also reduces some loops. Alright, and we do that for every single byte. I do a +0 here. You could also do bytes, of course, it's the same. Right, and then we obviously need to return from subroutine back to DOS, because I wanted to do the print TI $. Yeah, so this is basically how we carry the carry. Now, we do an explicit add 1 for the next one. You could do this, for example, add carry 0. That will actually add the carry itself to the value. But it looks a bit weird, and you then need to make sure to carry on anyways. It looks a bit weird, that's why I do add carry 1, but that is a definite possibility. Alright, so let's assemble this and run it and see how long it takes. My estimate is about 18 hours. And boy, was I off. So I drag the assembled file here into the C64 debugger. That way I also have some visual feedback. And yeah, this is pretty much as fast as a C64. Maybe a little tiny overhead, but not worth mentioning at these long times. So I first print the Jiffy timer, then I call our application in assembly that we just dragged in, and then print the Jiffy timer again. But I had the distinct feeling that it actually turned over, because the amount of time elapsed is incredibly long. Look at this, it's now 14:53 when we start this. Let's scroll to 1000 and see, yeah, this is our feedback. We're actually counting up, everything is working. And now wait. I played a lot of Cuphead in between and did a little bit of sleeping and other stuff that you do in the bed. And there we go. A whole day elapsed. It's 16:42 the next day. Fuck me. 25 hours and 50 minutes. Am I wasting my life? Am I wasting my last youthful years? I mean, I'm pushing 51. What the fuck am I doing? Waiting 26 hours to count to 4 billion. Unbelievable. Yeah. And we have to do it again, but now for the Z80. Where did my life come to? Why did I want to start a YouTube channel? I'm wasting the best last years of my life. Okay, let's jump in. So let's see how this would look at the Z80 running on the ZX Spectrum. And this is where the Speccy boys will laugh at us, Commodore people. And the Z80 fanboys will ridicule the 6502. Well, screw you. That is all I have to say, screw you. Because yeah, you do have the edge here. So let's assemble this at address 8000. We will load HL with 0, immediate 0. And we will load DE with immediate 0. We will loop. We will increment HL. And here comes a bit of the magic pasta sauce. Because if you increment a 16-bit register, also the carry isn't set. Or the jump 0, the 0 flag isn't set even. So we need to trick this a little. So the way that they do that in Z80, you load H into the accumulator, into A. Right, and then you OR L. So you OR basically what is in the accumulator with L. So when H contains 0 and L contains 1, because we already incremented it, and this just carries over automatically for you, then of course 0 ORed by 1 is 1. So it's not 0. So when it's not 0, jump relative, not 0 to loop. And now we're only counting, of course, 64 bits, because this is, 16 bits. This is 8 bits and this is 8 bits. So we need the other register. That's why we got this one. And this is a combined register of 8 bits in the E and 8 bits in the D. For all you people who have never used Z80 before. So we increment DE, Deutschland. And then we load A, the accumulator, with D. We do the same thing. And we OR the accumulator with E. Same thing here. If E is 1 and D is 0, 1 ORed with 0 is of course 1. Now if D also rolls over, so FF becomes 0, and then E is 0 as well, then 0 ORed with 0 is of course 0. And then you would end, but when it's not 0, we continue to loop. And otherwise we just return it, and with my assembler I need to do this as well. And that is it. So let's assemble this and run it. And you can see it's a lot simpler than with the 6502. So I assembled it and I'm loading it into Fuse. Unfortunately I don't know a debugger that shows the registers in real time for a ZX. But yeah, it is what it is. So we're loading it here. Okay, and it's running. And it's 18:33. So time for a shack, for some dinner. And, well, we'll wait and see. Hopefully not another 26 hours. Yeah, I moved the screen over just a little. And yeah, it's done. And it is now 3:32. That is 8 hours and 59 minutes. Only 8 hours and 59 minutes. Wasted. Waking up in the middle of the night. And I was lucky because I had my screen capture on. And I was like, nah, it's probably going to run for at least another 4 hours when I wake up. And I woke up in the middle of the night. And I checked and I figured, let's start the screen capture. I do my little midnight pee because that's what you get when you're almost 51. You have to get up in the middle of the freaking night and pee. I go back to bed, I wake up at 7 and I check, and 8 minutes later, then I start the screen grab. It actually ended the program. So if I hadn't woken up with my 50-year-old prostate pushing down on my bladder, I would have missed it and would have needed to start again and not be able to start the video now. So thank you, old prostate. Yeah, you keep on growing, buddy. You keep me waking up. Yeah, so 9 hours. Unbelievable. 9 hours to count to 4,294,967,296. 9 hours. So let's do it now on my mighty M1 laptop and see how quick we can do it there. Okay, let's do this quickly because we can. We tell where the source code starts. So in this case, in underscore start. We create a text segment. Text segment contains the code. We need to align it to 4 byte boundary. That's what the dotted line does for us. That is the way that ARM works, or most RISC CPUs. And this is the label where the operating system will jump to, because we told it to. And we're going to move into W0 the immediate value of 0, just like we did with LDA0 or LDHL0. And W0 is actually the lowest 32 bits of X0. So we are just going to use basically 32 bits of a 64-bit register. We need a loop, and now we need to add 1, and we need to add with 0-bit, that is adds. The S will instruct to work on the 0 flag. So we put the result in W0, we have W0 and we add 1 to it. So basically it says, what is in this register, add that immediate value to it and store it in that destination register. Easy peasy, right? if we did not wrap over back to 0, then the 0 bit isn't set, so branch not equal, because the 0 flag, the 0 bit, is actually the equal as well. Okay, yeah. And then we need an exit syscall, because we're here running in Darwin kernel, so we need to exit it. And in x0 is basically the exit value that we put. I just dropped it for the code, because I don't care what the exit value is. It's probably 0, because we're actually wrapping over here to 0 anyways. But who's to say what is in the top 32 bits? Okay, x16 by the way, right? And then we call the service routine x80 that calls the syscalls. So there you go. So number 1 here is basically the exit instruction. And this is the code. So let's first assemble it. Now link it. Alright, and then we run it. Let me put time in front of it, then we can see how long it takes. 1.498 seconds on average. 1.4 seconds. That was the average that I got eventually. That is significantly faster, right? 1.39, there you go. See, 1.4 on average. Wow. So there you have it. We have 2 8-bit powerhouses of the 80s count to 32 bits. And no, I refuse to ever say 4,294,967,296 ever again. It's just FF, 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 FF. That's far easier, right? And my goodness, did it take long. 25 hours and 50 minutes for the Commodore. Sure, if the debugger, say, has a bit of overhead, that would be those 50 minutes. Which I doubt, because my experience is that the debugger plays everything the same speed. But let's give it that. Then it's still 25 hours. That's insane. Now, sure, we could make this more efficient by paging out the kernel and the basic ROM. And then instead of going out to memory to count the individual 8 bytes into 0 space. Because that would be faster, it would save about 30%, I think. So maybe we'll do that in the future. Yeah, and the mighty Z80 did it in almost 9 hours. And yeah, the C64 PAL runs at around 1 megahertz. And the MSX ran around 4 megahertz. So that's your 1:4 ratio right there. But the main gain in the Z80 is because you stayed within the CPU, within even the same registers. So that is really where the gain is. And the same with the M1. We just used a 64-bit register, sliced off the bottom, turning the X register into a W register. And everything just stays within that CPU. And that is obviously a lot faster. So yeah, there is room for improvement in this. And maybe we will revisit it. Maybe it inspires you to do the same. Yeah, but I am impressed with these numbers. We are now 66,000 times faster than a CPU from the mid-70s. It's 66,000 times. It's incredible. It's mind-boggling. Yeah. CPUs are a marvel of human ingenuity and engineering. Yeah. So I hope you learned something, and see you in the next one.